Good evening, everyone. Am I audible? And is my screen visible to you all? Am I audible? Can you please write in the chat box? And is my screen visible? The screen I'm sharing right now. Okay, fine. So let's start the session. Welcome back to the fourth live session of Solar Energy Engineering and Technology. Myself, Soumya Tiwari. I am PhD scholar at Department of Sustainable Energy Engineering, IIT Kanpur. And in the this fourth session, what we'll do is we will learn about the basic or fundamental of the PV cells. Okay, or PV module. So as you can see, the assignment due date is 21st of this August. So what we'll do is we'll quickly go through the basics as we usually do in our class, and at the last of the session we'll solve some numerical problem. Okay. So till now what we have seen is the solar thermal application part. That was introduction of that solar thermal part. Now we are going to see about the solar PV part, so where the solar energy is utilized to basically convert it into electricity. So we'll deal about the PV cells, its construction, manufacturing process, working principle, what are the it's like various formulas involved with it, and I'll quickly highlight what are the important formula that you need to remember. uh, so let's start. So basically, for the devices that are used for this PV conversion are known as solar cell. So the basic building of any solar PV module is solar cell. uh, on this solar cell the radiation fall and it convert basically your solar energy directly into your DC electricity. So the advantage of this solar PV is that it has no moving part, require little maintenance, and it work both with the beam and diffuse radiation, and we can adopt it to for varying power requirement. But the main problem till now is that the efficiency of the solar cells are very low. So in the past few years, there are several um, R&D work, research and development work done to increase this uh, efficiency of solar cells, uh, thereby making it more affordable, like more cheaper. As the technology advances, the efficiency also increases. That leads to this more cheaper version of the solar PV cell. And thereby, if efficiency is low, the it's very cost intensive technology. Okay. So 90% of the current commercial production of solar cell are single crystal and the multi crystalline silicon cell. The application is varied from space to remote radio communication to lighting, powering, pumping. In Now your vehicle also have solar powered for battery charging. So these are various application. This is the history of this PV that I will leave. Uh, now, what is cell module and array? So to understand it in simpler language, solar cell is the building block, and the array of the solar cell make up a module, and the array of this module make up of array sorry basically a series and parallel of this module can be called as array. And this several arrays combined together is known as the whole PV system, with all its several other instrument involved, like inverter, battery, charge controller, DC isolator. Its whole thing is called PV system. Now, normal silicon cell has voltage of point 0.5. It's talking about a single solar cell, 0.5 volt and 20 to 40 milliampere per centimeter. So around, if you want to have a 2 ampere current, then around 100 centimeter of the solar cells are required. So how to get this 100 centimeter of square of this basically solar cell? We now combine it in the series and parallel form. That we'll see in detail how it is. What is series combination, what is parallel combination. Now this is the cell classification based on its size. So the standard size that we get is for the single crystalline and multicrystalline are 4-inch diameter or 100 centimeter square, or 4 by 4 inch square, or 5 by 5 inch square. So the thickness of this bulk silicon wafer are around 200 to 400 micrometer. And if we try to classify on the basis of like thickness, whether it is bulk material cell or thin film cell. Nowadays thin film cells are very popular R&D work, where several R&D work is going in thin film PV cell. If we talk about the junction, then it may be PN homo junction, hetero junction, or multi function cell, or metal semiconductor, or PIN, or like P type, intrinsic and N type. There are different type of depending on what junction we are talking about, and also based on active material. So it could be single crystal, multi crystal, amorphous. Now some compound gallium arsenide cell are also very popular, cadmium telluride cell, and organic PV cells. These are also like one of the active research work for this solar PV cell. Now so this is all the classification of solar cell, whether we're talking about silicon, compound, or organic. So in silicon we have crystalline, non-crystalline, or amorphous. In crystalline we have single, then poly. For compound we have gallium arsenide. Organic we have dye-sensitized and organic thin layer. These are all the classification, all type of what you have to have a quite knowledge or awareness about is what like what efficiency we are dealing with. So single crystalline have shown like maximum conversion efficiency. Single crystal silicon semiconductor solar cell 10 to 17%, and polycrystalline are a little bit less. And then amorphous, okay, gallium arsenide, this is the compound semiconductor which shows 18 to 30% conversion efficiency. Okay, this trend you can see with 1993 to 2017. How this solar efficiency from the past decades, how it has increased as the technology has advanced, thereby reducing this cost of this solar cell and making it more affordable, right? So you can see the multi-junction concentrator solar cell showing around 45, 46 percent cell efficiency. So okay, so coming to crystalline, polycrystalline, and amorphous. So as we know, crystalline means it's a very highly ordered microscopic structure. So in all the direction, the properties are unique, like its mechanical, optical, and electrical properties. Whereby if we talk about amorphous, where it has very short range ordered thing, so it's not like have same properties in all the directions. So due to the arrangement of basically atomic position in a given single crystal. Okay, so polycrystalline comes in between this crystalline and amorphous thing. So we have some order, but it's not regular in regular fashion in a long range. Okay, now this is basic construction of PV cell, single crystal silicon solar cell. So it's a screen printing method where this, if you see the construction of a solar cell, we have this backing layer on which with some electrical connection we have this P type silicon wafer and N type silicon wafer. So it's simple PN junctions, single crystal silicon solar cell with a non-reflective layer and your toughened glass, from where your solar radiation pass through this non-reflective layer onto this PN junction. Okay, so this is the basic construction, just to know. And if you gonna manufacture it in a simple terms, this whole process has been explained, that you have this P type silicon wafer placed on metal electrode like fingers, and here you have your metal electrode. So the screen printing of paste containing 70% silver organic binder and snitter glass is poured onto this metal electrode finger, uh, like in the space, and basically diffusion of n-type purity is done in this p-type silicon wafer, forming a p-n junction here. Okay, and basically a back for back contact, a paste containing aluminum is screen printed, and this all is placed in a furnace at 600 to 700 degrees Celsius. After that, the anti-reflecting coating of silicon nitride or titanium dioxide of thickness 0.1 micron is applied on the top surface, and then it's encapsulated in a thin, like, transparent material. So just to know how this simple basic construction and manufacturing process of single crystal silicon solar cell. And this is for monocrystalline silicon solar cell production process, that you can go by yourself. um, how silica with coke and how a trichlorosilane gas is used, separated, purified to get multicrystalline, and then melting and solidification to get your block of this single crystal silicon, and then with sawing we get a sliced silicon wafers, in which basically you're doping an electrical connection, same that we have seen in the previous slide, that is done to get your solar cell. Now, coming to working principle of solar cell. So in solar cell, basically what happens, we have positive charge and some negative charge, right? So positive charge, your holes are there, negative charge, your electrons are there. So we must have some cell that are made of material that can absorb the incoming solar radiation, right? Incoming solar energy uh, associated with the photons of the sunlight, and create this positive and negative electron hole pair, basically entities, right? And when we separation of this positive and negative charge by potential gradient within the cell occurs, that is the what we are seeking for. So this electron hole pair basically uh, uh, are the source or the cause of the potential we get across our PV cells, right? So this formula is well known, E equal to hc by lambda, where h is your Planck's constant, c is your velocity of light, and lambda is the wavelength of the incoming solar radiation, right? So as the wavelength increases, the energy corresponding to the photon decreases, and this energy is basically utilized to create the electron hole pair in the solar cell. So this is your valence band, this is your conduction band, and this is your band gap. So basically difference between the minimum energy of the electron in conduction band and the maximum energy of electron in the valence band is your band gap, and this is the amount of energy that is required to generate your electron and hole pair that will be gained from the incoming solar radiation. Okay. So semiconductor material like silicon, cadmium telluride, and gallium arsenide are the common PV materials of the solar cell. Okay. So I hope you know valence band and conduction band. Valence band has electron at lower energy level and is fully occupied, and conduction band has electron at higher energy level and it's not fully occupied. Thereby, on gain of energy, the electron from valence band uh, goes to the conduction band, leaving a hole here and generation of electron and hole pair. Okay. So now this P and N type. What is the P type and what is N type? P type are, if you want to correlate it, P type are say for positive, and positive are the holes, and N type is for negative, and negative are the electron. So in P type, what we have is we dope it by trivalent atom. Trivalent atom means like boron. If you see the table, okay, it's not given here. Okay, group C atom element, then when we dope it, then there is creation of a vacancy or a hole, and the P type of your solar cells are can be basically make an N type. We induce the pentavalent atom, so there are excess of electron like phosphorus, that basically makes your N type of solar cell. Okay. So N type has excess electron, P type has excess hole. When these two materials are joined together, excess electron from N type diffuses, and holes from P type diffuses, and these recombine and form a diffusion layer there, uh, and basically creates a built-in potential at the junction. So if you see, okay, it's not. So this This we will discuss in detail also. So for insulator we know that the band gap is uh, very large, so the incoming maybe solar radiation not enough to generate the electron hole pair, so there is no conduction of electricity. That's why they are called insulator. Right, in conductor we have excess of electron, so basically good conductor of electricity. In semiconductor it lies between insulator and conductor, that has the band gap but not enough that to generate an electron hole pair unless external energy is provided that is high enough to high enough than the its existing band gap to create a electron hole pair. So uh, you can see the energy band gap with temperature for gallium arsenide, arsenide, silicon, and germanium. So this basically band gap also is a function of temperature, and how it is related. This formula is important one. Okay, so fine. So this is the how band gap is related with your temperature. So at T equal to 0, material your behaves as an insulator. Okay, so simple numericals can be formed on this basically band gap correlation with temperature, such as uh, uh, band gap energy in silicon crystal at this 50 degrees Celsius. So note that this 50 degrees Celsius in this formula it's always have we have to put in Kelvin, not degree Celsius. Okay, so wherever we are dealing with we have to always put it in Kelvin for this solar PV thing. Okay, so EG0 is you're given 1.1 sorry EG0 that you can get it from table, right? This will be provided, this data will be provided to you, and just you have to put it all the values and you can get the band gap energy at 50 degrees Celsius, which is 1.1 electron volt. Okay, so similarly the optimum wavelength of light for PV generation in silicon cell. So we know this formula also that we have just discussed. When we put the h and c value, which is the constant value, then this formula can be simplified, and this formula you can remember, it's a very simple formula, equal to 1.24 by lambda. This gives the relationship between the wavelength and incoming energy of the photon. So if we want to like what is the optimum wavelength of light for PV generation, so for this you can calculate the value of lambda. Okay, now calculate the optimum wavelength of light for PV generation in cadmium light cell. Okay, band gap is given. So basically your note that band gap is basically your 2.42 electron volt, right? So we can we want some uh, so is you're given, lambda has been asked. This is the amount of energy that is required to basically generate the electron hole pair. So we will put the value of E and we can get the lambda value. Just a minute. Okay. Now the direct and indirect band gap. So to understand this direct and indirect band gap, K vector you need to know. K vector basically describe the crystal momentum. So if it is direct band gap material, so what is does it mean that the maximum of the valence band and the minimum of the conduction band, this is conduction band, this is valence band, occur uh, along the same k vector. Okay, so if electron have to excited from valence band to the conduction band, it has to follow a lesser distance, right? So it can be easily excited from valence band to conduction band without change in the crystal momentum. Whereas in conduction and if in indirect band gap, uh, electron cannot be excited without changing the crystal momentum. So photon here travel more distance before getting absorbed, and thereby this material must be sufficiently, the indirect band gap material must be sufficiently thick to absorb the incident light. Whereas in direct band gap material, we can have a thinner uh, like material that will be enough to absorb the incoming solar radiation. So these direct band gap will be more thinner, more lighter as compared to the indirect band gap. Okay, so now all the solar radiation coming onto the solar cell are not fully converted into your basically your electricity, right? Some of it is lost. So there are two most important loss mechanism. One is the inability of now all the incoming solar radiation, all the incoming photon is not necessarily converted into your electricity. So some are lost, or some has inability to convert the photon into energies below the band gap to the electricity. And the second loss is the thermalization of photon energy exceeding the band gap. So half of the most, like about half of the incident incident solar energy is basically lost in this conversion process. So the maximum energy conversion efficiency of this single junction solar cell is considerably below the thermodynamic limit. And this single band gap limit was first calculated by Shockley and Cossier in 1961. uh, so losses that has been explained in the next, I think, page. Okay, so so in this lecture, I think semiconductor basics are again um, focused on. Semiconductor is an element with electrical property between conductor and insulator, like silicon and uh, jelly, jelly. Okay, have four valence electron. Best conductor we have silver, copper, and gold, and best insulator have eight valence electrons. So basically, um, uh, it doesn't have any more like occupancy for another electron, right? So it's stable. Okay, so just a minute. This is okay. So silicon and germanium. Silicon is the most abundant element on the earth after oxygen, but refining process of silicon is very costly. So that we have already discussed how electron hole pair is uh, generated. uh, that we can, this theory part you can go by yourself. How like electron hole pairs are generated, how this recombination occur. So just you need to remember this point. Okay, so to develop the understanding, you need to understand this point. So at any instant we are talking about, there are three conditions that are coexisting. Okay, so there are always some electron hole pair creation, there is always some electron hole pair recombination, and there are always some free electron and hole existing temporarily awaiting for recombination. So uh, this slide basically develops the understanding of PV cells. Just a minute. Okay, so we know in an atom we have this nucleus and orbits around it. So each orbits have a different number of electron, that is given by 2n square, if you remember all the basic that we have studied. So each of this energy level can be basically equivalent diagram to this can be represented as shown here, uh, where in each of this radius of or in each this energy levels we have different electron. Okay, so it's not like we have a single energy level. Basically it's a band of energy level. So a band is there rather than a single energy level. This is because of various like number and various electron sizes that we have in each orbit. Okay, so that's why we have this energy band, not energy level. We have this energy band, first, second, and valence band and conduction band. So for every orbit there are billions of slightly different energy level that forms a cluster of band of this energy, that we use a term band like valence band and conduction band here. So okay, now semiconductor can be classified in intrinsic and extrinsic type of semiconductor. Intrinsic means we have very pure without any doping, where equal number of electron or hole pairs are there. And in extrinsic type, what we have impurities added, so it has been doped. So there is always excess of electron or either hole, depending on whether we are talking about n type or p type. So in n type, excess electron is there, and p type, excess holes are there. So if you see what we are talking about, so in earlier lecture, like so in n type, n doped silicon type, like we have doped phosphorus. Okay, so if you see here we have this excess of electron, and in p type we have injected say group 3 atom, that is maybe boron, and where it has one vacancy or hole in that, making it's p type semiconductor. So so the doping could be low, moderate, or heavy doping depending on what is the dopant concentration. This is the range signifying whether it is low doping or moderate doping or heavy doping. So now one very important term is this, the Fermi level. Okay, so first you need to understand what is Fermi level. So Fermi level basically tells that uh, uh, basically represent an energy state with 50% probability of it's being filled by a charge carrier. So basically it's a midway of 50% probability energy state, where the charge can be charge carrier can be filled or it cannot be filled. So there is 50-50 chance, a percentage probability percentage. So if you're talking about the intrinsic semiconductor, okay, so if we're talking about the intrinsic what's happening right now. So in intrinsic semiconductor we are talking about pure without any doping. So at thermal equilibrium the charge concentration are equal, so electron and hole pair concentration are equal. And if we according to Maxwell Boseman statistic, we have this concentration formula. Okay, so these two formula. So uh, basically your electron concentration is given in a term of this NCT e to power EF minus CC upon KT. So EF is your Fermi level energy, Fermi energy level, and EC is your conduction energy level, and EV is your valence band energy level. Okay, T is your temperature in Kelvin, K is your Boltzmann constant, and this NCT and NVT terms can be expressed in that we will see in the next slide. So if we multiply basically Ne into NH, it will be basically Ni square, and then we get this formula for intrinsic semiconductor, which is independent of this Fermi energy level. So this concentration factor Nc and Nv are given by these two formula, and that you have to remember because it will be used again and again. Basically this is for conduction band we are talking about mass of electron, and for valence band we are talking about mass of your holes. Okay, So the formula is same, 2 pi me kt upon h square to power 3 by 2, and here 2 pi m h, mass of the whole, kt upon h square to power 3 by 2. Okay, where we know the mass of electron 9.11 into 10 to power minus 31 kg, and mh is your mass of hole. So uh, the formula that you need to remember is this. So the Fermi level that, so this is your conduction band and this is your valence band. Okay, and this is your Fermi level with 50% probability that it might be filled with the energy carrier. So this is your Fermi level. So if you are talking about the concentration of electron, so concentration of electron, then it will be EF minus EC by KT. If you are talking about holes, then it will be energy of the valence band minus EF upon KT. Hope you understand how this formulas might have been derived. Okay, and in terms of only conduction and valence band, this formula, uh, so this formula you can remember, these two formula you can remember, and this formula you can remember. Okay, so this is another derivation for crystalline silicon at 300 Kelvin, and we can see this formula in term of conduction and valence band, and in term of effective mass of hole, and uh, your, this should be E. Okay, so this form, the important formula I have already highlighted, that you need to remember. Now if you talk about the extrinsic or doped semiconductor, then this, and concentration of electron and holes are not equal, they are different, and again this formula, not into p naught equal to n I square. So uh, basically, doping in pure semiconductor affects the carrier concentration and other electrical properties, and the Fermi level of n-type material and Fermi level of p-type of material, that again you can understand by, if this is your Fermi level and this is conduction band and valence band. So in intrinsic type, it is midway between your conduction and valence band. But if you're talking about n-type silicon, so there is shift of this Fermi level towards the conduction band, because there is excess of your electrons here. Okay, excess of electron, these are the electrons, and introduction of this new allowed energy level into the band gap due to this do, uh, doping. So this is your donor energy level, and if you talk about the p-type silicon, then there is excess of holes here, this Fermi level shift toward the valence band. Okay, and there is introduction of new energy level, this is your acceptor energy level. Okay, so you see how this Fermi level has been affected by, due to doping, whether in n-type or p-type. So in term of this Fermi level, for n-type material and p-type material, the Fermi level formula can be understand. So in term of n-type, we are talking about this type. Okay, where the Fermi level has shifted toward conduction band, it is energy of your conduction band minus kT ln nc by nd. So where your nc and nd are your effective density of state in conduction band, this is for conduction band, and this is your donor level. Okay, donor concentration or your donor density. And if you're talking about p type, then it will be ev plus kt into ln nv by nv, where nv is your effective density of state in valence band. Okay, and this is your acceptor concentration. Hope you understand, at least get some idea about how this formula might be derived. So you can, unless you understand how this formula might have been derived, it will be easier for you to remember these formulas. Okay, so the numerical will be based on this formula also. So we are talking about the p-type silicon has effective density of state in valence band. So what is given is effective density of state in valence band. So we are talking about effective density in valence band. It is given 1 into 10 to power 22 per centimeter cube. Impurity from the third group. So if we are introducing impurity from the third group, so there is this is p type. So you can relate, in p type we do the doping of third group, right, with concentration of 1 into 10 to power 19 per centimeter cube is added. Now if the band gap of silicon is 1.1 electron volt, find the closeness of Fermi level with the valence band. So what is it asking is Fermi level EF and valence band, right? EF minus EV. So what is the closeness? At the temperature of 27 degrees Celsius. So first you need to note that always put temperature in Kelvin. So it will be 300 Kelvin, right? Boltzmann's constant value, 8.629 into 10 power minus 5 electron volt per Kelvin. And this for p type, you know the formula. So for, energy of Fermi level will be equal to energy of your valence band plus kT into ln nv by na, right? So nv is also already given. Effective density of state in valence band. Your impurity doping concentration is also given. So na is also given, right? And your temperature is given. You can find ef minus ev in term of electron volt. So hope you understand how this formula is applied in actual numerical problem. Now this p-n junction, you can see if this animation is quite visible to you. So you can see that in p type we have axis of holes, in n type we have this axis of electrons seen by these dots. And electronic inhomogeneity is essential need for conversion of solar energy into electricity. So if you put this p type and n type of together, then there is formation of p-n junction due to basically holes goes from here to here and electron goes from here to here, and it recombine near this junction, okay, forming a depletion region. This is your depletion region. So this create a inbit potential at p-n junction. Okay, so the region formed due to recombination of electron and hole pair near the junction is known as depletion region. So a steady state is achieved when the built-in potential across the junction opposes the flow charge from the either side. Now this potential is enough to now prevent the flow of charge from either the side. So basically this is your depletion region, as I have explained, that is formed due to the flow of electron from n type and flow of hole from the p type. Okay, and this the basically movement of this electron and hole pair within this diffusion region gives rise to diffusion current. Okay, so in the space charge region, this depletion region or space charge region, the movement of electron and hole give rise to the diffusion current. And there is one more type of current in p-n junction, that is the diff current. That is basically generated when a forward bias or reverse bias has been basically applied across this p-n junction. So in forward bias we connect p type to the positive terminal, okay, and n type to the negative terminal. So it is forward because positive is connected to positive and negative to negative, right? So what it will do is it will basically this positive terminal will force this holes to basically move toward the n junction, okay, and similarly in n type electron will be forced to move toward the p junction. So these uh, current generated due to the biasing is known as the drift current. Hope you understand the difference between diffusion current and the drift current. And if the voltage in the forward bias is above the specified range, then the electron in the n region drift towards the through the junction and migrate to the p region, and the holes in the p region migrate toward the junction in the n region, which gives rise to the flow of current called the drift current. Okay, in reverse bias what happens is we are connecting p type to the negative terminal, okay, and n type to the positive terminal. So the uh, electron will basically flow direction will be this side, and your whole flow direction will be this type, and your electron flow direction will be this side. Okay, so basically electron get attracted to the positive terminal, electron get basically attracted to positive terminal, and holes get attracted to the negative terminal, thereby increasing this depletion layer. Okay, now this depletion layer will, what it will do is, it will increase this depletion layer. And after a certain particular voltage, what happen will, avalanche breakdown will occur through the PN junction, uh, resulting in a current to flow through the circuit. Okay, so I hope you understand how this reverse bias and forward, what happens in reverse bias, forward bias, and what is diffusion and what is drift current. Okay, so these are the generation. So in first, I'll quickly go through this slide. So uh, there are basically three generation of the solar cells material. And the first generation, what it was um, it was very costly technology, but mainly silicon based technology, single junction silicon cell with around 33% theoretical efficiency, but its energy conversion efficiency was around 15 to 20%. But it was very energy intensive and costly, basically technology. The second generation in develops where we started to use the amorphous cells, like cadmium tellurium and amorphous silicon and micromorphous silicon. So its efficiency was low as compared to the first generation, but the advantage was that the cost of production of this technology was very low. Okay, so like thin film technology came in this second generation only, where a very thin film of this silicon or glass or ceramics on substrate, this thin film material can be manufactured by various methods like spin coating, CVD, and etc. So the but the problem that of the second generation was its efficiency was very low. Then the third generation came with the advantage of both first generation and second generation. So what we have is a low cost technology with higher efficiencies. So the focus was basically focus was on improving the energy conversion efficiency and light absorption coefficient. And okay, so we are talking about the multi-junction solar cell as a typical example of third generation, and several incoming latest technology. Okay, so this was all for the, okay, lecture 10. The important part of this whole lecture series was this solar cell characteristics, the IV plot, the PV plot, uh, what is the dependence of I and V, I naught, VM, all the different terms that has been used here. You first need to understand those terms, and these formulas are quite um, they are derived, but for you have to remember most of these formulas. Okay, so you need to develop some understanding behind these formulas. So I will quickly highlight what are the important formulas that you need to remember. So if you are talking about simple PN junction, okay, it's not eliminated. So basically, if you are kept it in dark room, okay, at room temperature, so in that case, the current relation will be this I equal to I naught, where I naught is your reverse saturation current, e to power V upon Vt minus 1. Okay, this Vt is given by Kt by E. It is voltage equivalent temperature. Okay, so corresponding to particular temperature, a voltage will be there. That is the voltage equivalent temperature. and I naught is just reverse saturation current. So normally in dark, this is the plot of IV. So I is on y-axis, your current in milliampere, and V is your voltage. So in dark region, this is the characteristic plot of your IV curve. Okay, so so if we understand how this curve has been got, so I have explained just now that if p-n junction is, if in forward bias is applied, this will be your curve, this part of the curve. Okay, this part of the curve is in the forward bias. In reverse bias, that I have explained right now, that and after applying some voltage after a limit, an avalanche breakdown will occur, and the current corresponding to that is your I naught, your reverse saturation current. So this is for forward bias, and this is for your reverse bias. Hope you got how this curves and has been basically you got. Now if you are eliminating this p injection, now what happens is your uh, ISC term has been included. Those sign is negative, so this sign is basically negative because it occurs in the opposite direction, like the current. If we go to the terminology, it is ISC is in the opposite, so it is opposite to the flow of the electron, right? So this is your formula of p-n junction in elimination case. When the junction is short circuited at its terminal, then your in short circuit case, what is V equal to your voltage output is 0, right? And then if we put V equal to 0, this I will be ISC. Hope you get this V naught and I naught, and these simple terms. I hope you all are aware about. If you have any doubt, you can raise your hand and ask. Okay. Now you will come across this VOC and ISC term. These are very common term that you need to understand. ISC is your short circuit current, and VOC your open circuit voltage. Okay. So at ISC your V equal to 0, and at your VOC open circuit voltage your current value will be 0. Okay. So this formula you need to remember. Uh, this formula you also need to remember. Okay, open circuit voltage equal to Vt into Ln ISC upon I naught plus 1, where I naught is your reverse saturation current, ISC is your short circuit current, and your Vt is your voltage equivalent temperature. Okay, so if we're talking about room temperature, for ISC equal to 2 ampere and I naught equal to 1 nanoampere, then VOC found to be 0.55 volt. Okay, this is just a case. I think it's for silicon only at room temperature. Now this IV characteristics. So for energy source by convection, the current coming out of the positive terminal is considered as positive, and the mathematically the characteristics of solar cell may be written as this, that we have just seen, right? And this is your IV curve. So the if your V will be equal to 0, the this is your ISC value corresponding to V equal to 0, your ISC is here, short circuit current is here, corresponding to I equal to 0, your VOC is here, right? If you plot P versus V, so here it's power and here it's voltage. Okay, the graph will look like something this. Okay, so as you increase the voltage, the power will increase. After reaching some point, it will not further increase, it will further decrease. Okay, so these are for parallel and series that we will see later. And this point is your known as maximum power point, that that has very important significance in a solar PV cells, that we'll see later. So if you plot this both IV and PV plot in a single plot, then this plot we get. Okay, this is your IV curve and this is your PV curve. So ideally, what should be this curve should be looking like? So ideally, a cell should have this perfect rectangular characteristics. Okay, this perfect rectangular characteristic corresponding to its maximum operating voltage and maximum operating your current, but actually it's not there. So this is your real IV curve, say. So corresponding to ISC and VOC, right? So so to relate this actual solar cell to ideal solar cell, a fill factor is there. So there is a term that has been included, fill factor. Fill factor basically tells about the quality of the cell, how much close to the ideal this solar cell has been manufactured. So closer this IV curve to this rectangular characteristics, better is the quality of the solar cell. So mathematically, if we write this fill factor, it will be your Vm by Im upon your VOC by ISC. Okay. So for silicon, it's 0.5 to 0.83. And if we want to say the efficiency, instantaneous efficiency of the solar cells, so it will be P output upon P input, right? Normal efficiency formula is P output upon P input. P input to your solar power, which is your incoming solar intensity into your area of the collector, and your output is Vm into Im. Okay, so this it can be written in term of this fill factor also. So fill factor Vm into Im can be written is equal to Ff into fill factor into your VOC into ISC. So these two formula are important: fill factor and instantaneous efficiency. Simple numerical will be based on these simple formulas. Okay, and hope you understand the significance of fill factor. What is the I versus V plot? What is P versus V plot? What is fill factor? And how simple instantaneous efficiency formula can be calculated. So these two formula you need to remember. Now this is example of based on fill factor. So the fill factor of solar cell for which VOC, ISC, Vmax and Imax is given. Very simple formula. Fill factor is equal to the maximum voltage, maximum power that we can obtain, Vmax into Imax upon your ideal condition. So VOC into ISC. So fill factor is 0.34. See that the if it is closer to 1, then the quality of those cells are very good. Now the calculate the maximum power and the electrical efficiency of a solar cell at intensity of 200 watt per meter square, where VOC, ISC, Vmax, Imax, AC all is given. So basically maximum power is first asked. So maximum power is Pmax equal to V into I, that we know. We know Vmax value, you know Imax value, you can calculate the Pmax value, right? And the second thing is our electrical efficiency. So right now this we have seen this formula. So your efficiency is equal to output upon input, which will be equal to Vm into I1 upon Im upon your solar power, which will be IT into AC, incoming intensity into the area of the solar cell, right? So that you can put in the formula. So you can see the efficiency is 2.7%, very low, right? It's of a particular a single solar cell that we are talking about. Now this is the equivalent circuit diagram of an actual uh, single PV cell. So if you talk about the ideal condition, what it should be, this is your PN junction, right? This is your solar cell, okay, and this is your load we are talking about. So in ideal condition, the whatever we are getting should be we should be getting across the load also, but in real condition it does not happen. What we have is at the PN junction, even at the room temperature, if you are talking about, there is at the junction of p like p type and n type material, there is some contact resistance, right? So that resistance is basically represented in form of your series resistant. And even at room temperature, it's not like ideally no electron or hole pair flow is there. Due to some thermal agitation or something, or maybe material defectiveness, there is some flow of electron and hole. So corresponding to that, this shunt resistance has been basically incorporated to uh, basically signify those actual scenarios. So we have some series resistance, and we have this shunt resistance. So
Excuse me,
corresponding.
ma'am.
Hello.
जी ma'am.
Huh,
The numerical which you are taking before this slide,
okay.
please come there. This one output by input,
Right.
that is Vmax upon Imax upon incident solar radiation into area of solar cell.
Right.
I mean, how you can find this? Because P max is equal to minus 6 into 0.14, that is minus 0.84.
Okay.
Then what is the value put in here? Because I have calculated, then it was find 1.05%.
Okay. Let me check the uh, numerical the values that had been put here. So you're talking about the instantaneous efficiency. That value you have gotten different,
Yes,
right?
yes,
Okay.
G.
So basically, your input power is your solar power. That will be equal to the incident solar flux into your area of your basically solar cell. So it will be 200 watt per meter square into your 4 centimeter square. So centimeter square you have to put in meter square. So it will be 200 into 4 into 10 to power minus 4 meter square. So it will be coming into watt, right? So I think this part is clear,
Yes.
right?
Okay.
Now we are
Then
talking about the output, right? So in the
yes,
output we have Vm into Im. Okay. So Vm into Im, that you will put is 0.14 into minus 6 milliampere. Right. So you might have put this two value, right?
yes,
Right. Okay. So if you see the formula, so this is basically if fill factor has been included here, then this formula would have been correct. So since this fill factor has not been included, so this will be wrong. Okay. So thank you for pointing it out. Um,
yes,
I hope you got the whole point, right?
yes, yes.
Okay. So if you want to calculate into term of VOC and ISC, then you have to also include the fill factor formula, the fill factor value. Okay.
Okay.
Uh, so I'm happy that you have pointed it out. That shows that you have
Thank you.
understood the concept behind this formula. Okay. So I hope it's clear.
Yes, right,
Okay.
ma'am. Thank you, ma'am. Thank you very much.
Ah, thank you. So coming to this equivalent circuit diagram. Uh, so this for a practical cell, the characteristics of I and V can be uh, can be expressed in this term: I equal to IL minus I naught into this e to power V plus IRS upon VT minus 1 minus V plus IRS upon IR. So it's in term of series and shunt, and your IL is your photo generated current. Okay. And I naught you already know, just explained. So this formula, based on this formulas, the simplified version of this formula numerical will be based, but at least you should know how this series and shunt resistance come into the picture in the actual condition. And that I have just explained. I hope that is clear. Okay. So the typical value of series and shunt resistance are uh, mentioned here. So this is all the derivation, uh, the formulas that we have to remember. So basically, in this derivation, what it has been tried to uh, basically explore here is your how to calculate this open circuit voltage, uh, how to uh, get this ISC by I naught relationship. This is the important formula, and this is your important formula. Okay, so you will see how these formulas are applied in a. I hope in lecture you might have gone through this part, so I will not explain in detail because we don't have much time also. So the important formula for maximum current that you need to remember is this: maximum power you can already calculate Vm into Im. So if you know Im and you know Vm, okay. So we'll see how these formulas are applied. What are these terms? So as already explained, open circuit voltage. It is the maximum voltage that array can provide when the terminal are not connected to any load. We are talking about open circuit, right? So this value is much higher than the Vm, which relates to the operation of the PV array in is when its load is applied. Okay, ISC is basically maximum current provided by PV area when in a short circuit condition, much higher than the I maximum point that we are talking about at which the PV array is operational. Now this maximum power point, this is very important term. Its application is very significant in the PV cell. It's a point where the power supplied by the array connected to a load is at its maximum value. So it's corresponding to Im into Vm. Okay, so this is MPP, maximum power point. Okay, now fill factor. Fill factor, as I already explained, tells about the quality of the cell. Um, Fill factor gives relationship between the maximum power that the array can actually provide under normal operating condition. Efficiency, that we have already seen, ratio between the maximum electrical power to the amount of solar irradiance received. Now this is the IV curve. So now the voltage and current, this is the IV curve. Now the current depend on two important parameter. One is the intensity of the incoming insolation and another is the size of the cell. Okay, and this voltage depend on what is the material or type of the cell we are talking about. So this V is dependent on material, this I is dependent on cell size and the insolation. So as insolation will increase, incoming solar input is increased, your this your current will also increase. Okay, and as the size will increase, your current value will increase. That is well understood, I hope. And if depending on type of the material, this V can vary. So here you can see as the solar incidence is increased, the I value is increased, your solar radiation, your current will also increase. Because more number of electron holes pair will be generated and more current corresponding to that will get. Um, Now the maximum conversion efficiency of solar cell is given by ratio of maximum useful power to incident that we have already discussed. So for an efficient cell, it is desirable to have high value of fill factor. That means high quality of solar cells, right? High value of this short circuit current and open circuit voltage. So this high value of short circuit current is obtainable in low band gap material. So and high value of open circuit voltage and FF are possible for high band gap material. So in high band gap material, this V corresponding V is high, right? And in low band gap, this V is low, so your short circuit current value will be more. I hope this general understanding has been developed till now. This is a numerical based on the formulas that we have just studied. So the dark current density of silicon is at given temperature is given. The short circuit current density. Note that current density is given, the current is not given. Current density we are talking about. Notice the unit also, it's ampere per meter square. Okay, we are talking about current density, not current. Calculate the voltage and current density that maximize the power of the cell. What would be the corresponding maximum power output per unit cell area and corresponding conversion efficiency if the global solar radiation incident on the cell is given. Now also calculate the cell area required for an output of 45 watt. Okay, so what are given in the question is your dark current density. So I naught upon AC is given, current density is given, uh, ISC upon AC is given, and your temperature is given. Now voltage and current density corresponding to the maximum power. So VM and IM has been asked, right? So first you need to remember this formula. So these are the important formula that you need to remember. Okay, this will be directly applied in the numericals problem. So uh, basically, you know the ISC and I naught, ISC by AC and I naught by AC value. So if we divide these two value, basically we'll get this ratio only, right? And we know the temperature, we know the Boltzmann constant value, we know the E value. We can corresponding to that we can calculate the VOC value, right? Now this coming to this formula. So this VOC will be basically used further for calculation of other parameter. Now what you know is we know ISC, I naught, VOC. We need to know VM and IM. Okay, so we can use this formula that you need to remember. There is no shortcut to remember this formula. You have to apply again and again, then it will be incorporated in your memory. So we know all these parameters, ISC, I naught value we know. This VM, that we'll get this type of equation. So now to solve this type of equation, it could not be solved implicitly. So what we have to do is we have to do trial and error. So we have to guess some VM value, say start from 0.5, and we do hit and trial method until this equation is satisfied. Corresponding to that VM value that satisfies this equation, that is your VM value. Okay, now we got the EM. So for maximum power density, we have this another formula. We know the VM value, I naught value, ISC value, AC value. In term of basically density is asked. So it's IM by AC only. Okay, so you can put all this value, you can get the IM by AC value. So maximum power will be your VM into IM that you have just calculated. So it you'll basically multiply these both parameter to get the maximum power. And for maximum conversion efficiency, we already know the input intensity, right? It's 865 watt per meter square. So that is your input power, and your Pmax is already in term of your density is given, right? Watt per meter square. So we can divide both this parameter to get your maximum conversion efficiency, which will be equal to 13.46%. And if you want a power output of 45 watt, so your P output is given, and corresponding to that area has been asked. So you know the intensity value, you know the power output value, we already calculated the efficiency value. So corresponding to that, your area of your solar cell can be calculated. So this is how this, what formula are important, how it's applied, how to calculate this. This gives the basic understanding of all the formulas that you have uh, basically uh, basically read till now. Now, okay, so I'll quickly explain this effect of solar cell temperature on solar cell efficiency. So the temperature basically affect the solar cell efficiency. So higher the temperature, higher will be losses to the surrounding. So because there will be more difference in temperature of the solar cell to the atmosphere, so there will be more losses, and thereby this temperature affect this solar cell efficiency. Now if you uh, do the energy balance, so alpha is your absorptivity of the solar cell, tau is your transmittivity. So we have a cover onto the solar cells from which your solar cell is passing by, and then this is your, says your PN junction on which it is absorbed. So there is tau corresponding to this cover, and absorptivity corresponding to this solar cell. Okay, so this is equal to your whatever if electrical efficiency into plus your losses. So UL is your over losses between your temperature of the solar cell cover to the atmosphere. So this energy balance, I hope it's clear how it's written. Now another important thing is your NOCT. It's nominal operating cell temperature, that is taking corresponding to 20 degrees Celsius, 800 watt per meter square solar irradiance, and 1 meter per second wind speed at no load condition. So at no load condition, basically we are not getting any power across the load. So your NC will be 0, and then we can switch here and there and we can get this formula. And this is how the cell temperature can be found for the your solar cell in term of this parameter that we have just studied. So this formula, actually this formula you can remember. So if we talk about how electrical efficiency is a function of temperature, so electrical efficiency is your electrical efficiency of solar cell at standard test condition, your STC, right, into 1 minus B naught. B naught is your silicon efficiency temperature coefficient, that is a fixed value, into TC minus 298. TC is your solar cell temperature. So this is your efficiency and temperature relation. Now that we can see how that you can go back into lecture and see this slide. uh, this slide is important. What is effect of variation of insulation and temperature? So as insulation increases, your current value will increase, your power will increase. So this is the trend that follows for the IV and the PV curve. And uh, the so if you see here, the increase with increase in temperature, what happens is your band gap reduces and more photo generation current will be there. But there is also increase in the reverse saturation current, thereby the there is very marginal increase in the current as compared to the increase in voltage. So if we'll see this volt, as we increase the temperature from 25 to 60 degrees Celsius, there is very marginal increase in the current as compared to the voltage, and due to which your fill factor decreases. Okay, so fill factor decreases. This fill factor is basically area between this basically curve, IV curve, right? So this fill factor decreases and your power also decreases. So the new the effect of variation of temperature on the characteristics of solar can be given in term of this. So this is your new ISC value. So if earlier this was your ISC value corresponding to 25, then this will be ISC dash. Okay, for which this formula is given. So you need to understand how the temperature affect the your current density, your voltage, your your power, your efficiency, and your fill factor. These dependency or you should understand and you should be aware about. Okay, so these are all the data value. I will skip this slide. And now coming to PV module. So solar cell combined together to form a module. So it's basically a series and parallel combination of this solar cell. And how this series and what is the effect of combining this solar cell in parallel and series, that will basically learned in this particular lecture. Okay, so as you know that the bare single cell cannot be used for outdoor energy generation because output is very small for a particular cell. And so for workable voltage and reasonable power, we have to interconnect this appropriate number of cell. So the most common module have series connection of 36 silicon cell to make it capable of charging 12-volt storage battery. So if we combine this solar cell in series, what happens is your voltage increases, right? That affects the voltage. If we combine in parallel, then your corresponding current value increases. So if this is your IV curve, okay, so if this is your normal IV curve. So if you for a single cell, if you combine two cells, then your in series, then your voltage value will be two times this of VOC. If it's three cells are connected, it's 3 VOC. If we connect two solar cell in parallel, then current value will increase, right? Corresponding to 2 and 3. So This classification is based on the back cover, so whether it's glass to Tedlar or glass to glass or semi transparent, and that you can go through. So if we go to the market, how what specification are given for a module. So this is the table that shows in a market or in a basically commercialized PV cell what specification are given. So normally weight, size, number of cell, output voltage, output nominal output, voltage, maximum voltage, VOC, IC, and conversion efficiency are given. And these are for the standard test condition, that is 1000 watt per meter square, air mass index 1.5, and cell temperature 25 degrees Celsius. Now, there are some practical difficulties associated with PV module. There could be a cell mismatch, or also there might be effect of shadowing also. So partial shadowing of cell in series connection or in parallel connection. We'll see one by one each of this thing. So cell mismatch means you're manufacturing a bunch of solar cell, okay, in a batch, or maybe in several batches. So it's not like all cells will be identical. Ideally, it should be identical. This VOC, ISC, VM, and IM value should be identical for all the cells. But in practical condition, it's not same. So there is some mismatch also. Okay. So what is effect of this mismatch? So in actual condition, uh, in ideal condition, the P combined, the power combined should be the equal to the power combined sum of individual cells, but in actual it's always less than that. So if it's connected in series, then what happens is, um, in series, the cells are bound to carry the same current. So the current value will be same, but your it will the fill factor of the combined IV curve will be reduced. In parallel, if there is mismatch, the voltage are bound to be the equal, but the current value will decrease. So to reduce the mismatch loss, what it should be, so from the same batch the different solar cell be taken, and the cell sorting should be done correctly. Well characterized cell should be cell characterization should be there according to its matching parameter, including the specified tolerance, so that the given module should have most appropriate cells with matching specifications. Now, effect of shadowing. So basically, partial shadowing have significant consequence on the output of solar cells. So these are different solar cells. If this solar cell is say partially shadowed, then what happens is, this is in series connection, right? So the current value that we are getting will be limited by this solar cell, because this will dictate now what is the maximum current value that we can obtain from the total module, because the whole current has to pass from each of this solar cell in the series combination. So to avoid this, and also due to this shadowing, what happens is your it's not generating the desired energy from the solar cell. Also, it also heat up, so that leads to additional losses of the generated power. Okay. So uh, and it can also further, if temperature is high, then it might lead to cracking and several problem also. So to avoid this, in parallel effect of shadowing in the parallel series connection, what we do is we basically add diode to each of the solar cells. So what this diode does is, it uh, basically says that if the voltage corresponding to this particular solar cell is negative, it will not allow current to pass through this uh, basically diode, and if it is positive value, then only it will allow the current to pass this basically diode. So it's like bypassing this particular shadowed solar cell, such that it will not affect the performance of other solar cells. So now this, due to addition of this diode, this is not the limiting parameter or the limiting cells. Now if the cells are connected in parallel, so uh, partial shading is less a problem as compared to the series, because the current generated in particular solar cell need not to pass through every solar cell connected in parallel, so they are independent. But the problem with uh, so you will say that okay, we'll not connect in the series, we'll only have the parallel connection only. But there is also limited limitation to this parallel connection also, because for a module consisting of say 36 cell in parallel will generate a very high current combined with very low voltage. So the voltage corresponding to each solar cell connected in parallel will be same. Okay, so the voltage value is less, the current value is very high. So the if the resistive loss in the cables, that will be very high in the parallel combination case. So it's not like we can combine all the solar cell in the parallel only. So there is limitation to that also. So to avoid it, we need both the combination, series combination also and parallel combination also, with inclusion of the bypass diode. Okay, so one bypass diode for every 18 crystalline solar cell is provided. So if the typical 36 cell module is there, so it has two bypass diode in a particular terminal box. So this is the just explained. So for parallel, it's added in basically series, and for series it's added in the parallel. So that you can go through. Now here comes the packing factor of the PV module. So it's if this is the rectangular PV module, it's not like its whole area is covered by the solar cell. So if the solar cell is like this and the second solar cell is like this, it's not like the whole PV module. So there are some left basically area between each combination of the solar cell. So the packing factor defined as the ratio of total solar cell area to the total module area. Okay, so it will be always less than 1. Okay, and so the efficiency of the PV module, electrical efficiency, can be expressed in term of these three terms. Okay, so one is the tau g. Tau g is basically transmittivity of the glass cover. Beta c is your packing factor, and electrical efficiency is your eta n. So the uh, so this formula, I hope this is clear how these parameters are included. um, Now uh, the temperature dependence is also explained similar to the formula that we have seen earlier, 1 minus beta naught Tc minus 298. Okay, beta naught it as STC condition. So this is the formula. So numerical. Okay, so we have few minutes left. So well, so I'll quickly explain this. A PV system utilizes a power a DC motor to produce 2 horsepower shaft power. Motor efficiency 85%. Each module has 36 crystalline silicon cell arranged 9 cross 4 matrix. Each cell size is given, cell efficiency is given. Calculate the number of module required in the PV array. Assume the global irradiance as 950 watt per meter square. Okay, so each module has 9 cross 4 solar cell. Each cell size and efficiency is given. We have been asked how many these type of modules are required enough to power this motor, which has some its own efficiency, and the output power is 2 horsepower. So 1 horsepower is 735 watt. So this is actual power that is utilized, but this is your output power. But the motor has some inefficiency also, so the input power for this motor will be your output power upon your efficiency. So it will be your 1470 by your this efficiency of 0.85. So the actual input power that has to be generated here is by the solar PV is your this 1729.4 watt. Now to generate this much power, how many module of this solar cell has like you have to is required. Okay, so the area of each solar cell is given is 0.125 cross 0.125, and this is area of each solar cell. There are 36 solar cell in a module. So multiplied by 36, and say there are n number of modules. So this is the actual required area to generate this much amount of power. Okay, so if you put into the equation for the conversion of this PV module, then it will be output upon input. Input is your incoming solar radiation into this area, and output is your this required power. Okay, 1729. So if you put all this parameter, you can calculate the number of module. I hope the concept behind this question is clear. Um, the next part is very important, the MPPT part, maximum power point tracker. So uh, um, the gist of this MPPT is that we are trying to operate our solar cell always at the maximum power. Okay, so for that we do the load matching. So either we can do mechanically track the sun, so that uh, uh, we are operating at the maximum power point, or we can electrically also track the maximum power point. So this can be done by this buck boost converter controller sensing and logic unit. So what we do is, um, if I quickly explain you, we want to always operate at, this is your IV curve and this is your sorry, this is your IV curve and this is your load curve, okay, corresponding to different loads. So ideally we want to operate always at this point, this load, okay, this corresponding to the maximum power point. So for that what we do is, we basically interpose an electronic maximum power point tracker between the PV system and our load. And how this MPPT works is that uh, uh, we incorporate a buck boost converter. So what buck boost converter does, it can vary the voltage and current, and it can increase and decrease the voltage and current, such that this voltage and current voltage changes such that voltage and current changes such that the maximum the PV cell always operate at the maximum power point. So some feedback mechanism is also involved. So these are the three strategies by which this MPPT might operate. So say for this case what we do is, we current, so this is your PV curve, right, if you remember. So we current change the current value. So the buck boost converter, this is a switch, okay. So what does this switch does is, we can on and off the switch, uh, that will allow whether the current will pass or not. So say for the a duty cycle is there. So a duty cycle is basically says for how much time this switch will be on and for how much time this switch will be off. Based on the time for which this switch will be off and on, uh, a corresponding voltage will be there. Okay, so we will see corresponding to this change in voltage how this power output is varied. So if the power dp by dv value is in negative region, so the feedback mechanism will run such that it will increase in its value until this maximum power point is reached. Or if it is in positive region, then it will basically uh, feedback mechanism will run as such that dp by dv point equal to 0. This point maximum power point is tracked. Okay, so this is the, okay, we have 10 minutes. So um, this this is say this is your source and this is your load. Source is, say this is your PV panel, okay, and in between source and load we have incorporated this MPPT. So a PV source is supplying power to a load whose line intersects with the IV characteristics. So this is your IV characteristics, this is the load line. The point at which this IV characteristics and load line intersect, that value is given 20 volt 6 ampere. The voltage and current at the maximum power point. So the maximum power point is this point, right? So the voltage and current corresponding to this point is also given. Determine the additional power gain if the MPPT is interposed between the source and the load. Consider the efficiency and cost of MPPT are 93% and this much rupees. For how long does the system need to operate in order to recover the cost of the MPPT? Assume per unit cost of electricity to be rupees 65. So if you want to know what is the power produced without MPPT, it will be simple, your 20 into 6, right, corresponding to this load line. This will be the your power produced. What is the maximum power production capability of the PV system? So the maximum power that will be correspond to this maximum current and voltage, that we know. But what is the actual power produced with the MPPT? So that will be equal to your this 200 value into your efficiency of this MPPT. Okay, so this maximum power point, power value into your efficiency of this MPPT. This is the actual power produced. Now, what is the surplus power produced when the MPPT? So this is without MPPT. This is without MPPT, and this is with MPPT, right? Including the efficiency of this MPPT. This is the value. So the surplus power is this value minus this value. This will be 66 watt. And if you talk about surplus power for T hours, then in kilowatt hour you can basically manipulate it, and the cost corresponding to it will be multiplied by 6.5 of per unit cost of the electricity. So the time required to recover the cost of MPPT, which is 3500, that will be equal to this will be equal to 3500, and then from here you can calculate the T time. Okay, so hope this question is clear. uh, okay, so I have few questions. So this is the first question. I have how many minutes we have? We have few minutes left. So I request you all to solve this question. We have some few question only. We'll discuss. Try to wrap up within 10 to 15 minutes. So since we have not much time left, what we'll do is I will show you the answers. So the correct option is this, C, 0.05 watt. So what we have been asked is the power output from a solar cell under STC condition, 1000 watt per meter square, 25 degrees Celsius. Efficiency is given, fill factor is also given, and the aperture area is also given. We know the formula for efficiency. We have Vm into Im upon your incoming solar radiation into your area. So uh, so this can be also written in term of fill factor into your EOC into ISC upon IT into A. So the power output from the solar cell, this has been asked. So you know the efficiency value, you know the IT value, you know the area value. You can put it into the equation and you can get this power output value. Okay. The second question is simple question. What is the most common material used in making solar cells? Right. So the most common material is silicon. That is the correct answer. The electrical output of solar cell depends on the intensity of solar radiation, heat component, ultraviolet radiation, infrared radiation. So the correct answer for this question is A only, intensity of solar radiation. Uh, it does not need to be a heat component, UV, IV. We are just talking about the intensity of the incoming solar radiation. Now, the electrical efficiency of semi-transparent PV module is uh, more than opaque PV module, equal to the opaque, less than the opaque, or none of this. Just don't be confused about the terminology. Try to use the common general knowledge of what is opaque and what is semi-transparent. You will understand the question. Right. So in a semi-transparent, more incoming solar radiation will pass, right, as compared to the opaque PV module. So glass to Tedler and the glass to glass PV module we are talking about. So it's more, the semi-transparent glass to glass is more efficient, electrically efficient than the your opaque PV module. Now, this is the question. Two solar modules are connected in parallel, having voltage rating of 12 volt each, with a current capability of 3.5 ampere each, respectively. What will the output be in term of voltage and current? Right. So we are talking about two module connected in parallel, right? So each has 12-volt rating, and current value from each module is your 3.5 ampere. So if we talk about this whole system, your output voltage will be 12 volt only, right? And your current will be your 7 ampere. So this option D is correct. Now the Fermi level is close to conduction band in that dash type of semiconductor and close to the valence band in. So if you remember the diagram that we have seen in intrinsic and extrinsic type, so this is intrinsic, this is N, say, and this is P type. So the Fermi level is midway. In N type, excess of electron, this is so conduction band, okay, and this is your valence band. So in N type, it is Fermi level is shifted toward the conduction band, and in P type, it's shifted to your valence band. So the answer will be your N type and P type. Okay. Now this is the one numerical problem. So I will read out the question. A solar cell of area 4 centimeter square. Okay, this is 4 centimeter square. Receive a solar radiation with a photon energy of 1.8 electron volt. Uh, Having the intensity is given 200 watt per meter square. Measurement show open circuit voltage. So the open circuit voltage is given 0.24 volt. Short circuit current is given 10.24 milliampere. Okay, and maximum current is given, im is given 6.5 milliampere. uh, Efficiency of cell is also given 1.1%. What is the maximum voltage? Okay, so for that, this is uh, since we have not any time left for this session, uh, I'll quickly explain it. So we know the efficiency formula, which is equal to your Vm into Im upon Voc into Isc, right? Uh, this is given. This is given. Max is given. Voc is given. Isc is given. We can calculate the Vm value. Okay, that will come to 0.135. Now the second term is fill factor is asked. Okay, fill factor, you know that. Oh, sorry. This is your fill factor, and your formula for efficiency is your Vm into Im upon Isc, your incoming solar IT, say, into your area, right? So your area is given, your IT, this value is given, your efficiency is given, your Im is given. You can calculate Vm by this formula. Okay. After getting Vm, all these parameters are given. You can calculate the fill factor. So hope this numerical is clear. So the answer will be 0.357. Okay. So the hope you have understood the theory and the formulas part. The so the basic requirement from this module was to you to get to know what are the different parameters, and what are the different terminology, how these formulas are correlated, what are the important formulas, um, what are so the question will be similar to what question sir has solved in the lectures. So the pattern of the question will be similar to that, and also similar to the assignment that you have been given. And I think whatever the numerical sir has explained in the, or whatever the lecture content that sir has delivered in the those these modules are enough to solve the this basically your uh, assignment questions. So I hope this session was useful to you. And okay, thank you all for listening. If you have any doubt, feel free to drop your question in the and answer your portal in the Swayam, or asked in the next slide, next lecture. Sorry. So I hope this session was useful to you. Thank you all for listening. We'll see you all in the next session. Thank you.